the organisers for giving me the opportunity to present today. The work I'm talking about is joint work with Dan Archdeacon, Nick Kavanagh, Jeff Dinitz and Shule Yazici, and a number of other people have worked on Heffter arrays. Ian will come up during the talk and he's worked on Heffter arrays with Jeff Dinitz as well. Okay, so because it's late in the conference, I'm only going to give you a general idea of what we've done. A lot of the proofs in this area involve a lot of basic arithmetic, so they're not terribly interesting to plod your way through, but what I want to give you is a general feel for what we've done. So this is the only slide that has a definition on it. There will be a few other slides which have some theorems on it, but otherwise we're generally going to look at examples. So, what is a Heffter array? In its most general form, a Heffter array is an m by n matrix that satisfies the following properties. So, we are going to take S filled cells per row and T filled cells per column. So if we have m rows and S filled cells per row, that means we're going to use fill m times S cells, and so we want m times S distinct symbols. So, we're going to take the set 1 to ms and we're going to distribute these symbols throughout an array such that we have either x or minus x, one or other. So each symbol in the array is distinct and it's either positive or negative. And we want to distribute these entries throughout our array such that there are S filled cells per row and T filled cells per column, but we want to do it in such a way that every row and every column sums to 0 modulo now 2 times m times s plus 1. Okay, so these are examples down here of Heffter arrays. These are called square Heffter arrays because we've got the same number of rows as columns. And the other distinction is that if we have every cell filled, then we call our Heffter array tight. And if the sum of our rows and columns is exactly equal to 0, not 0 modulo 2m times s plus 1, then we call it an integer Heffter array. So here, this is in a square array. We have 4 rows, 4 columns. We have 3 entries per row and column, and it's integer because the sum of each row and column is exactly 0. This over here is once again a square Heffter array. It's a 6 by 6. K gain is 3, so we have 3 entries per row and column, but it's no longer integer because if you look at the last row and the last column, the sum is not 0, but it is 3 6s are 18, doubled is 36, plus 1 is 37. So that's the definition of Heffter arrays. Now in general, in this talk, we will talk a little bit about tight ones, but just talk about what results are known. Mainly we're going to deal with square ones. I'm going to start by telling you a little bit about what's known about integer Heffter arrays, but then I'm going to go on and focus on these ones where we're interested where the sum's not equal to 0, or what is equal to 0 modulo that big number. All right, so what are the origins of Heffter arrays? Where do they actually come from? So most of us know Hefter's first difference problem, where he said, is it possible for a positive integer n to partition the set 1 to 3n into triples, such that those triples have this property. The sum of the 3 entries is 0 modulo 6n plus 1, which is double 3n plus 1, or the sum of two of these is equal to the third entry modulo 6n plus 1. So that was Heffter's first difference problem. And what we're saying here, if we're looking at a square integer Heffter array, where k is equal to 3, so 3 entries per row and column, we want to end up with sets of triples, 3 per row, 3 per column, such that the absolute value of the entries in this triple partitions 1 to 3n, because we're allowing negatives, okay? And we want the sum, though, of the entries in this triple to be congruent to 0 modulo 6n plus 1. So it's a similar idea, except for we want simultaneously two sets. So the rows are going to give us one partition, the columns are going to give us another partition. That's a Heffter array. So this is a solution to Heffter's first difference problem. When n equals 2, we're partitioning the set 1 to 6. And this is a Heffter array where we've got a 6 by 6 array and 3 symbols per row and column. Okay, so that's just a little bit about the origins of the problem. Why are these sorts of objects interesting, in particular Heffter arrays? Well, Dan Archdeacon back in 2014 drew the connection between Heffter arrays and bi-embeddings. So let me just tell you what a bi-embedding is, and then I'll come back to the result. So if we take an embedding of K7 on a torus here, then we can decompose the graph into triangles such that these triangles are two-colorable. So yes, it's a Steiner triple system. Each set of purple triangles gives me one Steiner triple system. Each set of white triangles gives me another Steiner triple system. And this is a bi-embedding of two Steiner triple systems. So that's the general idea of a bi-embedding. So what did Dan Archdeacon do? He said, well, if I have one of these Heffter arrays and it has some extra properties, which I don't really have time to tell you about, but if my Heffter array has some nice extra properties, then it gives me an oriental embedding of k2m times s plus 1, such that every edge is on a face of size s and a face of size 2t. So in other words, it gives me a bi-embedding of a set s cycle system with a t cycle system. When I think about k times 2m times s plus 1 being bi-embedded in an orientable surface. So if I've got these Heffter arrays, if they have nice properties, then I can move into this topological graph theory and think about bi-embeddings. So that's why they're interesting. I think I'm going to run out of time, so I'm going to skip this slide. Okay, but it tells you a little bit about the history of bi-embeddings. I just want to, so it started with Heffter, and I want to focus on this little result here. And Young's in 1970 showed that it was possible to bi-embed a pair of cyclic Steiner triple systems in an orientable surface if n was congruent to 7 mod 12. And then in 1974, Ringwald showed that it was also possible to bi-embed a pair of Steiner triple systems if n was congruent to 3 modulo 12. So the importance of that result is that we use the way they bi-embedded the Steiner triple systems to get some Heffter arrays. But before I tell you about that, I want to tell you about what's known about Heffter arrays. So remember, this was type meant every cell was filled. Integer meant the sum of the rows and columns was exactly 0. And in 2017, Archdeacon, Boothby and Dinitz showed that it was always possible to construct tight integer Heffter array provided m and n were greater than or equal to 3 and m times n was congruent to 0 or 3 modulo 4. If you drop off the integer and you just looking for tight arrays, then it's still possible. Then in 2015, this is Dan, Jeff, me, and Shule Yazuchi. We show that it was possible to construct some square integer Heffter arrays for certain classes. We didn't get them all, but then Jeff and Ian finished it off. And so this is counting arguments that give you this condition here. And so we've been able to show that for all admissible values, there exists square integer Heffter arrays. So square integer means that you're taking the sum of each row and column to be exactly 0. So if you drop off that integer condition, you're saying that the sum of each row and column should be congruent to 0 modulo n times k, 2n times k plus 1. So you think, all right, that's another degree of freedom, and it should be easier to get the non-integer ones. That's what we were thinking. So the non-integer ones are here. Yep. And they're the cases we were considering. All right, so now how did we construct some of these integer Heffter arrays? Well, we went back to Young's and Ringel's work, and we looked at the way they were constructing the bi-embeddings of the Steiner triple systems. So they used 3 regular bipartite graphs that were ladder graphs, and there was a current assignment on each of the edges in this graph, and it satisfied Kirchhoff's law, and that was that the sum of the labels at any vertex was congruent to 0 modulo a particular value. All right, so this is a bipartite graph, so we could assign one set of vertices to be the rows. We could assign the other set of vertices to the columns, and then we could take these labels and distribute them throughout the array. So this is column 2, and it has 26. It actually has minus 15 and minus 11, and they are the entries we put in column 2 of the Heffter array. So taking the labels on this ladder graph, which was constructed by Young's, we could take this information and turn it into a Heffter array where there were 3 entries per row and column. And in fact, it turns out that these sums, as long as you're using positive or negative integers, these sums are exactly 0. So this is how we got integer Heffter arrays when k was equal to 3. So what happens though when k is bigger than 3? So what do you do? Well, it's possible to just add a pair of diagonals to the empty cells like this, and you can do it in such a way that you haven't mucked the sums up too much, all right? But if I add another set of diagonals, I can bring it back to being right, so that the sum of the entries, the 4 entries here, these ones here sum to -1, these ones sum to +1, and overall I haven't changed the sum at all. So once we had our Heffter arrays for k equals 3, then it was possible to add 4 extra entries per row and column and keep our sums equal to 0. So we could go right through the range of values there. What you notice here is that these diagonals actually form something like a Hamiltonian cycle. If you're thinking about the rows as being a set of vertices, the columns as being a set of vertices, then these cells give me a Hamiltonian cycle down through the bipartite graph. So what we've really done here is added adjoined two Hamiltonian cycles such the sums in this cycle cancel out the sums in that cycle, and so overall I have not changed the sum of any row or column. All right, so that was integer Heffter arrays, and essentially doing that in some other constructions which are a bit more complicated. And Ian and Jeff got some when k was congruent to 1 modulo 4. We completed the spectrum for integer, square integer Heffter arrays. So when they're non-integer, then we're looking at these cases here, and this is the possible range of values. So what I'm going to focus on is this one here. First of all, I'm going to take p equal to 0 and just show you how to construct Heffter arrays, which have 3 entries per row and column. Okay, and then once again, I'm going to take it up. So, remember that for our integer case, we had these nice ladder graphs. They don't exist for the values that we needed for the non-integer case, but what we were able to do was show that you could split them up. Okay? Take that ladder graph and carve it up. And so what's happening here is that's what we've done. We've taken the ladder graph, carved it up, and you'll notice down here, we've got all these sums here equal to 0, all these sums here equal to 0, but down here now, the sum is congruent to 0 modulo, in this case, 2 times 19 times 3 plus 1. Okay, also what's happening here is this is the biggest values. We have to, 37, 3 times 19 is 37, so we're distributing the integers 1 to 30, no, sorry. 3 times 19 is 57, and we're distributing the integers 1 to 57, and these are the big numbers down here, and they're being used to give us these sums, which are not exactly 0. Now, to complete the spectrum, we have to be able to add at least 4 entries per row and column, all the way through to almost n. How do we do that? Well, first of all, we change these. Oh, what I should say is, okay, so in the non-integer case, we could just add 4 diagonals and the sums cancelled each other out. But that's not going to work here, because if we do that, we'll be adding 0 to this. But now, we'll have 19 rows and columns, but 7 entries per row and column. So we're no longer working modulo 115, we're working modulo a bigger number. We thought this would be easier, and in fact initially we all ignored this step and said, no, we're not interested, that'll just work, no. And then suddenly Shule was doing some examples and she said, oh no, it's not working. We've got to do lots more down here. And then we all thought, wow, that's the end of this, we don't know how to do that. But we figured out ways to do it. So we changed those big numbers, in this case, down here. So we've got to add an extra 4 entries per row and column, and we change them to the big numbers that we want. They add up nicely. Now we can put in 4 entries per row and column, and they can all sum to 0, because everything's back to being right. What's important here is that extra 4 diagonals we're adding are sort of giving us 2 Hamiltonian cycles which are cancelling each other out. All right, so essentially that takes care of the case when k is congruent to 3 modulo 4. How difficult does it get? Well, here's another construction we got. This is when k, the number of entries per row and column, is congruent to 2 modulo 4. What's interesting about this is this construction is just working on diagonals, but where we're either increasing or decreasing by adding 6 to the entries as we go down. So each of these diagonals is a modulo class here, and it comes out very nicely. But the sums down here now are all 2 times n times k plus 1, or modulo, 0 modulo that. So now what do we do? Because when we add an extra 4 entries per row and column, we've got to increase this sum. We can't just have these 4 entries summing to 0. So in fact, it turned out that what we wanted to do was negate all of this, end up with negative numbers down here, and then add lots of really big numbers, and it all came out to being okay. How complicated does it get? Well, in the integer case, when k was congruent to 1 modulo 4, that was the case that we really struggled with, and that Ian and Jeff got in the end. Once again, it was a case we struggled with here. So the solution to this case is the numbers here. This is a Hamiltonian cycle that we could add, but we have to be more careful here, because the Hamiltonian cycle, to increase this from 5 to 9, has to avoid certain entries. So it gets more complicated. It even gets more complicated than that as well. But I'm not going to go through those details. Essentially what we've proved is that now there exists a Heffter array with square Heffter array, which is an n by n matrix with k entries per row and column for all possible k in this range, and under the condition that n times k is congruent to 3 mod 4. So that's the result we've got. Okay, just finishing off, I wanted to thank you for listening and to say happy birthday to Charlie, and I know Charlie's not in the room, but both Shule wanted to come. Only thing is, she's sailing around the the Marmarin Sea, I think. So she just couldn't make it. And Jeff was trying to get here, but got turned back. And I have a message, so both of them say hi to everybody. And I know Charlie is not in the room, but I want to read out Jeff's message because it tells you a lot about their relationship. So Jeff said, working closely with Charlie as handbook editor, fellow department chair, co-authors on papers, and co-editors of the JCD has been a true pleasure. He is a true scholar, and I wish him the best for many, many more productive years. So I will pass that on to Charlie as well, but I thought maybe you guys might like to hear it coming from Jeff. Oh, well, in fact, Jeff was very disappointed because he had enough of those t-shirts printed for all the editors of JCD, and he thought on Tuesday night that you could have all worn one, and he was very disappointed that he couldn't bring it. Yeah.
Unfortunately, there is no time for questions. The next speaker, let's thank again